Hi everyone, I am Patrick Poon from NTU Singapore. First of all, I would like to thank Du Yungs for his invitation and the organizers for overcoming many difficulties to conduct this conference. Today, I would like to share with you my research about optimal intervention of interest rate. And this is a joint work with my former postdoc, Rachana. So this problem is not new to the OR or economics field. And the first paper, maybe this one, published in 1999 on how to intervene the foreign exchange rates. So for the similar problem, it assumes that the central bank can intervene the interest rate or exchange rate at some cost, while the central bank has the objective to remain the rate at a target level. So our aim is to find out what is the optimal timing and the intensity of the intervention. So such a problem is usually solved with the impulse control approach, which is developed in 1970s by Benselsons and Lyons. And you can see there are many applications of the impulse control in finance and OR covered here. So here I would like to stress that what we cover later on in this talk will likely to be extendable to these other problems as well. So the problem we are interested in is the optimal impulse control of the interest rate. And the concerns that we would like to bring up is the modeling of the interest rate, because the best results, to the best of our knowledge, is to handle the optimal impulse control under the local volatility model. And that is published in this paper in 2014. And it assumes the interest rate to follow local volatility model. But under such a structure, such a quite general structure, the impulse control relies on the computational method. And in our paper, we would like to fill in the research gap by considering the stochastic volatility model. And stochastic volatility models is not completely new in finance, and it's actually commonly used in modeling stock price as well as the interest rate. So you can see a lot of papers provide empirical evidence that SB modeling is good for interest rate. So that is our motivation. And under the stochastic volatility model, the impulse control problem is extremely difficult to solve. And perhaps if we step back a bit, looking at the ordinary stochastic control problem under SB model, we may also find difficult to find the explicit solution. So now we will introduce powerful and practical tools called SB asymptotics. So it was first used in option pricing, and such asymptotic technique is especially for solving the PDE problem. And the technique is systematically documented in this book. And it was recently applied to portfolio optimization and other papers conduct the error analysis. So the recent development is to incorporate it into constrain the stochastic control problem and also conduct the error analysis on it. And here, what we want to do is to consider stochastic volatility models for the impulse control problem and derive the SB asymptotic solution. So we will also establish the accuracy results for the derived asymptotic solution. So in this table, we distinguish the contribution of our work and some other highly related works. The first one also consider impulse control, but we are different in the type of models we consider and also the type of the solution. So ours is more on the analytical solution, and we are making contribution from a mathematical perspective. So for the bottom two, the main difference, of course, is that they consider the ordinary stochastic control problem and we consider impulse control problem. And the second key difference will be either the the duration of the problem, or how we identify the first order correction. So basically, in order to derive the asymptotic solution to the impulse control of interest rate, we have to overcome a few difficulties encountered in different papers. So let's take a look at the model we assume for the interest rate. So the model is highlighted in this, is presented in this equation 1. And I would just like to highlight a few features here. First, we incorporate mean reversion feature of the interest rate. And second, for the diffusion term of the interest rate, we assume another stochastic process for the GT. GT is the stochastic volatility. And the ROIs are correlated. And on top of that, we have the intervention at the end of the process of the RT. So tau I is the intervention time, and the Ci is the intensity of the corresponding intervention. So you can see that we introduce the delta into the SV process GT, and we assume the delta to be very small. Because what we want to do is to develop the asymptotic solution under this model. And to this end, we assume the stochastic volatility model is slowly varying. So why we want to do so? Because we know that when delta equals to 0, GT is just a constant. If GT is a constant, the volatility of the RT is also constant. So the optimal impulse control of the interest rate under constant volatility has been studied by other people. So there is a solution. And what we want to do is to deal with the optimal impulse control problem under model equation 1, perturb around the solution corresponding to delta equals to 0. So that is the starting point of our problem, of our study. So here is a formal definition of the impulse control. We use T and C to denote the control policy. And as we mentioned, the central bank has the objective to remain the interest rate within close to the target interest rate. So that's why we have the running term in our cost functional, running cost. So we use the quadratic cost. And for the second part is about the penalty on the intervention. So we actually have two asymmetric penalties for increasing the interest rate and decreasing the interest rate. So they could have different penalty. So now what we want to do, what we need to solve is that we find the time and also the action, a series of them, to minimize the cost functional J given in the equation 2. So to study this impulse control problem, we need some technical assumptions to make sure that about the regularity of the impulse control problem. So we basically need this, and these are quite common in the impulse control literature. And after that, we will be able to define the value function, which is the optimal cost value after we have taken the optimal impulse control. And the value function is something we want to solve for, as well as the optimal impulse control, which is highly linked to the solution to the Corsi variational inequalities. So we first introduced these Corsi variational inequalities, and you can see some things common in the control literature, like this one is something like HJB equation, but this one is to refer to the continuation region, and this one is the action region. So the solution to this is linked to V by this verification theorem. So this theorem tells us that if we can solve for the QVI and it satisfy these two conditions, then the value function is greater than or equals to this V delta. And if the corresponding impulse control is admissible, then it will be the optimal impulse control, and V will be equals to V delta. So this verification theorem is first established in this paper, and we need to just do some minor adjustment due to the addition of the SV model. So now our focus can be shifted to solve the SQVI. of course, after we have the solved for the QVI, we need to check whether they satisfy these two conditions. But the concern of this paper is about how to solve such a QVI. So to solve for the QVI, basically is also very difficult. And the usual way to solve it is to propose a suitable anxieties. And one suitable anxieties for the optimal impulse control policy is the band policy. So it is characterized by D, capital U, and U. So basically, this I would like to introduce this band policy using this graph. We are going to monitor the interest rate. So if the interest rate hit the lower bound small d, then we will put it back to the capital D. And if the interest rate hit the upper bound small u, we will put it back to the capital U. So we basically force the interest rate to stay within the D and U. Or in other words, if it stay in D and U, we do nothing. If it is outside D and U, we are going to put it back to the safe band, capital D and capital U. So using such anxiety, we can actually convert the QVI problem to this free boundary problem. So we can define the so-called action region, just like what I described. And the value function outside, in this action region can be easily found by this equation, right? Because we are going to take action. When we take action, you will pull back to the value function at capital D plus the penalty. So if we stay in the continuation region, then that means we do nothing on the interest rate, then the dynamics of the V delta can be characterized by the Ito's lemma. So that's why we have the first equation, and the boundary conditions also come from the conditions given in the action region. So since here, when we try to solve for the QVI, we are looking for a classical solution, which means that the solution we found should be smooth. So that's why we have the desire to have this V delta in C1, and that's why we also impose these smooth pasting conditions. So this free boundary problem together with the smooth pasting condition would fully characterize the V delta, small d, small u, capital D, capital U. These are the 5 ingredients we would like to solve for. So this will also give us the optimal impulse control. So this problem is difficult to solve due to the due to the fact that the LSV is very complicated as it involves the stochastic volatility model. So we apply the SV asymptotic technique to solve. So the idea of the SV asymptotic is to consider expansion form for the V delta as well as the boundary. So we use a generic notation here, P, and we expand it according to the order of the square root of delta. And in this study, we are only interested in the first 2 terms, which is V0, V1. V1 is the first order correction, P0 and P1. So the difficulty of applying SV asymptotics on the free boundary problem is we also need to expand for the boundaries. Or if we put the boundary as something in indicator function, then we need to also expand around the indicator function. So to this end, we leverage the lemma 3.4 in this paper. And this basically tells us that if we expand the indicator with respect perturbation term, we just need to extract the 0th order term. So this is actually also common in the asymptotic analysis for American option pricing. So this is actually not surprising, but previously the lemma 3.4 was not used. So now we can expand the free boundary problem as well as the smooth pasting condition. So in order to determine the 0th order solution and the first order correction solution, we just need to extract the 0th order terms and also the first order terms respectively. So let's take a look at the 0th order term. So if we take all the 0th order terms, then we will have this free boundary problem together with the smooth pasting condition. So this problem is actually not new and not surprising, because as we discussed, this problem corresponds to the impulse control problem when delta equals to 0, right? And this problem has been studied in this paper, and almost all the solutions are existent already. So I'm not going to spend much time on this. So zeroth order solution can be written explicitly. And one of the major mathematical merits of this paper is to derive the first order correction term. And after we taken all those first order terms from the full FB free boundary problem, we will find this one, drive the V1 is also a free boundary problem. And the difficulty stems from the non-homogeneous term here. And we need more lemmas. So these two lemmas are very useful, and they are new to the literature. So this one tells us that basically the first lemma is used to derive the second lemma. The second lemma tells us the relation between the figure and gamma of the V0. So the homogeneous solution of the V0. So it is very important because the set dependency of the V0 is hidden, is implicit. So calculating the partial set actually poses extremely difficult analytical challenge. But this relation tells us that it can be written as something in terms of the second order derivative with respect to R. So using these two lemmas, we will be able to derive the V1. And after we derive the V1, we can also derive the P1 from the smooth pasting conditions. So far we have already reviewed the zeroth order solution as well as the first order corrections. And next, we are going to review some properties about this solution. And the first one is actually inspired by this paper, which conjecture that even without the first order correction to the optimal policy, the zeroth order band policy can also result in the optimal value up to the first order approximation. So in order to see this, we can actually investigate the realized value function using the zero order strategy. So we denote the realized value function as V pi 0. And then we can find that the PDE, the V pi 0 is driven by the free boundary problem here, a fixed free boundary problem with fixed boundary. So we do the same expansion. We can find that each zeroth order and the first order terms will be consistent with our V0 and V1. So that actually gives us some ideas about using zeroth order strategy may really can recover the optimal value up to the first order. So next, we are going to prove this rigorously. So to this end, we actually need quite a lot of technical assumptions and quite a lot of tedious analysis. And we also make some assumptions. We actually point out some examples in which the assumptions are satisfied. So if you're interested in the derivation, the tedious derivation here, you can refer to our paper. And the results I would like to show you is that if we have all those technical assumptions, then the order between the V pi 0 and the first order approximation will be bounded by delta times a constant function. So I think this is a very rigorous error analysis. And for this result, I would like to remark that it is even good for other families of the strategy of different expansion form, because one may criticize that such a good result is tailored to the expansion form we consider. So to get rid of it, we even consider this family of the expansion form. We don't expand, we consider a more general family, and beyond the expansion using square root of delta, we use delta to the power alpha. And basically we repeat what we have just discussed, and we can also obtain the accuracy results, and all the things can be summarized in this table. We found that actually, in short, U alpha equals to 1/2 will give us the best accuracy already. So that's why we are okay to just use the expansion form we proposed previously. And finally, I would like to highlight a few things about this paper. First, we brought the SV into the impulse control problem, and we derived the SV asymptotic solution as well as yeast error analysis. So this is the first paper to do so. And the takeaway message is that is also for practitioners. You just need to use the moving zeroth order band policy that will give you the optimal value up to the order square of delta. So the future work can consider other SV settings for sure, and even consider the fast mean reverting SV, fractional SV, and Wolf volatility. I think those will be some promising future research. So that's all for my research. Hope you like it. Thank you very much.